Welcome. In this example, we're going to take a look at a flow known as a Poiseuille flow. Let's go ahead and write down the name here, Poiseuille. Let me just verify that I spelled that correctly. I'm pretty sure I did, yep. Poiseuille flow is just named after the scientist who first investigated this kind of flow. We're going to define what that flow looks like. It's basically flow in a circular pipe. So we have a pipe, it has some diameter, capital D. Let me put a center line in here. So the diameter of this pipe is capital D. The walls are fixed. It's infinitely long, so it continues on for infinity there. We're going to make a number of assumptions along the way just to define what this flow looks like. So the first thing is it's a pressure-driven flow. So the fluid is moving because there's a higher pressure on one side of the fluid than the other side. So let me write this out and then I'll describe it a little bit more. And we're going to say that the pressure gradient driving the flow is dp dz, and we'll say that that's a constant. The z direction here is this direction right here. And we'll say this is a radial direction, r is that way. So just to put a little coordinate system on it. So it's a pressure-driven flow that dp dz is, if the flow is going from left to right, then dp dz is less than 0 because it means that the pressure is dropping as you move in the positive z direction, right? So that pushes the fluid from left to right if dp dz is less than 0. But anyway, we'll just say that dp dz is constant here. We'll ignore gravity. You can actually incorporate gravity into the analysis, but for simplicity here, we'll go ahead and just ignore it. We're going to say the flow is fully developed in the z direction. What that means is that the velocity profile does not change as we move in the z direction. So whatever the velocity profile looks like here, it's going to be the same velocity profile here, same velocity profile here. That makes sense. If the pipe is infinitely long, there's no reason one part of the pipe should look any different than the other part of the pipe. Okay, so that's what fully developed means, is that the velocity profile doesn't change. We're going to say that the flow is steady. So we're at steady state. So that means that we just don't have any variations with time. We're also going to say that the flow is axisymmetric with no swirl velocity. So axisymmetric flow. That just means that there's no variation in the theta direction. The theta direction would be, rotations about the axis there. So we don't have to worry about any variability in the theta direction. And we'll say no swirl flow. What I mean by that is that the theta component of the velocity is 0. So we don't have any flow kind of swirling its way down through the pipe. It's all, what we'll see is that the flow is all just going straight in the z direction. Okay, and then we'll say, let's see, I'm trying to think if there's anything else. I think that's it for now. Oh, actually couple more. We'll say that we're dealing with an incompressible fluid. So we don't worry about variations in density. And we'll also say it's a Newtonian fluid. So that gives us a relationship between shear stresses and the velocity gradient. Again, you can relax these assumptions, but we're going to make them here for the classic Poiseuille flow makes these assumptions. Okay, let's go ahead and get started. The way we're going to analyze this is with a differential control volume. So we're going to look at a small control volume and apply conservation of mass and the linear momentum equation to that. And then using those expressions, we'll derive what the actual velocity profile will look like. Okay, so that's the plan. We're using a differential control volume to derive the velocity profile. So the control volume that we're going to use is going to be a little annulus. And I'm not much of an artist, but I'll try to do my best. So we're going to have a little annulus here that kind of looks like this. There's like it's very thin in the z direction, and it goes around at a certain radius, but it's a kind of a thin annulus. I'm going to redraw it down here to make it a little easier to see. So let's see if I can do a good job at that. So here is what it looks like. Okay, and then this will be radius r. It's definitely out of proportion here because that's r, and this thickness here is dr. dr is just this thickness right here. Right, so it's out some radius r and then dr. dr is supposed to be very, very small, but I exaggerated the dimensions here just to make it a little easier to work with. And we're going to say that this dimension here is dz. Because this is a tiny little control volume. It's a little displacement in the z direction up here. It's a little bit here in the r direction. And then we're going to go ahead and apply conservation of mass and linear momentum to that control volume. So let me go ahead and do conservation of mass first. Let me do it in a different color first. There we go, conservation of mass. We'll write it out. And then we'll go ahead and evaluate each term and then simplify the equation. Okay, so this first term is the time rate of change of mass inside this control volume. So it's all the mass inside there. But keep in mind, we're saying that we're dealing with a steady state situation here. So nothing should be changing with time. And in fact, there are a couple of reasons this whole expression will actually be equal to 0. Number one is that it's at steady state, so there is no variation with time. And then the second reason is that the density is a constant because we said it was incompressible. And then the volume doesn't change with time because we're using a fixed control volume here. That control volume is not expanding or contracting or moving around in time. It's just fixed in space. So that's not changing with time either. So for all of those reasons, that first integral here, the time rate of change of mass in the control volume is 0. Now let's evaluate the second term. This is the mass flow rate out and into the control volume. So that's going to happen from the left side and then out through the right side. So the way we're going to handle that is we're going to say right at the very middle of the control volume, it's a little hard for me to show here, but right at the very middle here, we're going to say that the z velocity is uz and the r velocity is ur. It's right at the middle. And so on the front face, and I'm gonna redraw the picture because it might be a little easier if I redraw it. So we're gonna look at it straight from the side. So this is my dz. And I said right at the middle, the velocity is uz and ur. So the velocity coming in from the side here is going to be uz plus duz dz times minus dz over 2. And then on the right side, it'll be uz plus duz dz times a positive dz over 2. The idea here is that if we say that the velocity is uz at the center, and I don't know what that velocity is, we're trying to derive what it is. But if I say it's uz at the center, then if I move to the left just a small amount, that distance is dz over 2, then what it'll be is the velocity I start with right at the middle, plus how that velocity changes as I move in the z direction, that's duz dz, times how far I've actually moved to go from the center to the left. So I moved a distance of minus dz over 2 because the positive z direction is that way. Right? So that's what the velocity is on the left-hand side. The right-hand side, it's much the same. It's the velocity I start with, plus how the z velocity changes as I move in the z direction, times how far I've moved to go from the center to the right side. And that's a distance of positive dz over 2. Okay, hopefully you understand that. Now in the r direction, now you might know just in advance that there's no flow in the radial direction in this geometry, and that's okay. But I'm going to pretend I don't know that yet. So now we're looking down the axis of the pipe, and the velocity, again, I'm saying that I'm going to say that the velocity right here at this point in the radial direction, I'm going to call that velocity u sub r. Ignore what I said before where I said it was u sub r right at the center. we'll just say it was u sub z at the center there. Let me redraw my control volume there. Okay, and then I'll erase it here as well. Okay, so for the UR velocity, I'm going to just do kind of the same idea, but I'm going to say it's UR right here at that radius R. Remember, this has some radius R here. And then the thickness of this thing is dr. So if it's UR right at that point, then the velocity here will be a little bit different. It'll be UR plus dur times dr times how far I've moved. In this case, it's a positive dr. Hopefully that makes sense to you. It's the same idea as what I did up here, but I'm just using starting at a different point. I'm saying it's UR at radius R, and now as I go from here to here, the velocity's changed a little bit. It's the velocity I start with, how that radial velocity changes as I move in the R direction, times how far I've moved. Right? I've just moved a distance dr to head out that way. So that's what my velocity on the outer surface is. The theta direction I don't have to worry about because I said that this was an axisymmetric flow with no swirl velocity. So that part I don't worry about. All right, so now I'm ready to actually write out what my conservation of mass expression looks like, or specifically the mass flow rate term. So let me write the mass flow rate term in the z direction first, and then I'll worry about the radial direction. So on the left-hand side of the, in the z direction, let me just write it out and then I'll explain it. So like I said, I'm going to write the whole thing out and then I'll explain what each term is afterwards. So there's a lot to write, so just be patient. Okay, I've got everything I need here. So let me go through each term and explain what they are. So the density terms, you can see all the densities here. Remember, we're saying we're dealing with an incompressible flow, so we don't have to worry about variations in the density. This is the velocity coming in through this left-hand side. And remember that our control volume is fixed. So when I have the relative velocity, that's normally like the fluid velocity minus the control surface velocity. In this case, the control surface velocity is 0 because the control volume is fixed. So it's just the fluid velocity. So this is the fluid velocity right here on this left-hand face. And then this is the area through which that fluid velocity is traveling. That's this area. Let me highlight it in the picture. I'll highlight it in green. It's this face area that the velocity is traveling through, right? So fluid's coming in through that green face. And that area there is going to be 2 pi r, that's the circumference, 2 pi r, times the thickness of this, which is dr. So that's that one. And then when I do this dot product between the velocity and the area, it gives me the negative right here because you can see the velocities to the right and the normal area, the normal vector for the area n hat would be to the left. So that's what gives me the negative here. Excuse me. Then I can do the same thing on the right-hand side, right? So on the right-hand side, I've got the density right there. The velocity is here. Remember, it's this velocity. And then the area is the same area. It's 2 pi r dr. But when I do the dot product there, because the normal vector is off to the right, it's in the same direction as the velocity. So that gives me a positive. Okay, so that's the mass flow rate term through the kind of left and right faces. Now let me do the radial faces. So this is the mass flow rate through this inner face in the radial direction. So here's the density. There is my velocity there, it's UR. This is my area, that interface. It's just this circumference, 2 pi r, times the distance in and out of the page, which would be the dz. That's that one. And then we have the negative because the normal vector on this face is acting, it's an outward pointing normal vector, so it points in the opposite direction of u sub r. So that's why we have the negative. And then we'll do the outer face. So again, we have the density. Here's the radial velocity at that point. Remember, it's a little bit different because we've moved from the inner surface to the outer surface. This is the area of the outer face. Again, it's the circumference, but in this case, the circumference is 2 pi times r plus dr because it's a little bit bigger circumference than the inner one. And then dz is the thickness in and out of the page. And when we do the dot product, we get a positive because the normal vector for the area points outward, and so it's in the same direction as the velocity. All right, so hopefully that makes sense to you. Well, it turns out we can simplify this expression a bit. You'll see there are some terms that cancel out. For example, this uz and that uz cancel out. And then these duz, dz terms actually add together because you've got a negative and a negative here. That makes that a positive, and so then that'll add together with that one. In these expressions, we get, it's a little more complicated because we have to multiply those out. So I'll do that separately in just a moment. So let me rewrite just that control surface integral. We'll have duz dz times, it'll be 2 pi r dr times dz when we simplify these two terms together. And then let me go ahead and expand this whole thing and simplify it. So we'll have a minus rho ur 2 pi r dz. Then we'll have a plus rho ur times 2 pi r dz plus rho ur times 2 pi dr times dz plus rho dur dr times dr times 2 pi r dz plus rho dur dr times dr times 2 pi times dr times dz. Hopefully I did all my algebra. Basically this, this whole thing here is just expanding out this term. Let me just quickly review it to make sure I've got all the parts right. So just tedious. I think I got it all correct. Hopefully I didn't make mistakes. Okay, so now let me look at that and see how I can simplify things a bit. First of all, you'll see this term cancels out with that one, so that's good. That makes that a little bit easier. And then this term here is special because you'll see that this has a dr times a dr times a dz, whereas these terms are just a dr times a dz, right? So this one is actually much, much smaller than these terms because it has an additional differential term, right? This has 3 differential terms. Remember, these differential terms are very, very small. So if I multiply 3 very small quantities together, it's much, much smaller than having 2 small quantities multiplied together. So this one is negligibly small in the limit as these become differentially small quantities. So this we call a higher order term. So it just means we neglect it. It's very, very small. Okay, so then let me go ahead and substitute these things back into conservation of mass. So substitute into conservation of mass, and then we'll simplify. So again, this first term here, that was just 0, so we don't have to worry about it. This term, it just comes down to be this and that and that. So we'll just expand that out altogether. That whole thing should be 0. So duz dz times 2 pi r dr dz plus rho. Oh, by the way, I think I forgot a rho here. Yeah, when I expanded these two terms and added them together, I forgot the rows. So let me add that in there. That goes in the front. Sorry about that. Okay. I'm to that point now, so let's go ahead and try to reduce this further. What you'll see is that in each one of these terms we have a dr dz, dr dz, dr dz. We also have a 2 pi term in all of these and a rho term. So we can divide through by all of those because in general those aren't going to be 0. So let's go ahead and do that, and then we'll be left with uz dz times r. That's this first term. The next one will be just u sub r. And then the last one will be dur over dr times r. Put the r there. Okay. So we're getting there. We're simplified things a little bit further. We have one more thing that we can do here. This one's a little bit tougher to see, but if you look at this for a long enough period of time, you'll see that you can combine those two terms together as just taking the derivative with respect to r of r times ur. Right? If I expand this out using the multiplication rule, I take the derivative of this one, which would just be ddr of r is just 1, and then multiply it by ur. That gives me this term, and then I can take the derivative of ur with respect to d over dr, that's this, and then multiply it by the r there. So you can see I can write that a little more compactly. So what this gives me in the end is r times duz dz plus d dr u sub r is equal to 0. So this is what I'm getting from conservation of mass. Okay. Now at this point I'm going to use one of my assumptions that I expressed earlier on. So let me go all the way back up here, and you'll see that I said that I had a fully developed flow in the z direction. That means that the velocity profile does not change as I move in the z direction. So what that means down here is this term I can set to 0. So that I'll say is 0 because it's fully developed in z direction. Right? So I just carried it through, but it eventually was 0. So now I'm left with just ddr of r times ur is equal to 0. I can integrate that once with respect to r, and so I'll get r times ur is equal to a constant. So that then tells me that ur is a constant over r, right? So it varies inversely with respect to r. Okay, now if you look at that for a moment, we'd have to apply some boundary condition to figure out what that constant is. Well, let's think about this. We have our pipe flow. Let me redraw it again here. This is the radial direction. Well, we know immediately, first of all, we don't expect there to be an infinite velocity along the center line, right? When you have a pipe flow, you don't have infinite speeds on the center line. So when r is 0, this just becomes undefined. It goes off to infinity. So that doesn't make any sense. We can't have that. So that means that C1 would have to be 0. The other way you can think about it is out at the boundary here. We'll call that capital R out to the outer radius. We know that we have no flow through the walls. So it has to be 0 there as well, which would also mean that C1 has to be 0. So in both cases, we know that C1 has to be 0. So C1 equals 0 since the magnitude of UR is finite. So let's just write it as finite. That's the center line comment. And we can also say and UR at R is equal to capital R is 0. So for both of those reasons, C1 has to be 0. So that means there's no radial velocity. So UR is everywhere 0. Again, we sort of knew that going in, but I just wanted to derive it and just show you can get it from conservation of mass. So that means our flow is going just in straight lines in the z direction, right? So it's fully developed, so it's not changing in the z direction. There is no swirl component. We talked about that as one of our assumptions. And now we know there's no radial component. We get that from conservation of mass. Okay, now let's move on to see what the linear momentum equation gives us. So we're going to use the same control volume up here. It'll look like the same picture here, but now we're going to apply the linear momentum equation in the z direction to that. So let's write that out. Again, there's just a lot to write, so let's spend a few moments and get it all written down. Because my coordinate system and control volume are fixed in space, I don't have to worry about any acceleration term in the linear momentum equation. So in general, there'd be like an acceleration term at the end of that equation, but since our coordinate system is fixed, our control volume is fixed, we don't have to worry about that, that term. Okay, let's go ahead and simplify, or at least expand what each of these terms comes out to be. So the first term is going to be 0. This is the time rate of change of z linear momentum in our control volume. That's 0 because it's, again, steady state. Nothing is changing with time here, so we don't have to worry about that. In addition, we know that the density is not changing with time. The velocity there, I'm sorry, the volume is not changing with time. We know that the z velocity isn't changing with time. It's again steady. It's all steady state, so that's why that's 0. Let's go ahead and evaluate the linear momentum flow rate in and out of the control volume. This one I'm going to, well, let me just write it out. We know that the z velocity does not change in the z direction, right? So let me go back up here. Let me just write a few things out here. So in general, the z velocity could be a function of what? Time, radius, theta, and z, right? Just in general, right, the velocity could be a function of time and position. But we say that we're dealing with a steady state flow, right? So we know that it's not varying with time. We said there's no swirl component, or it's axisymmetric, I'm sorry, it's an axisymmetric flow, so there's no variation with theta, so that we get rid of that. We know that the flow is fully developed in the z direction. That was our assumption up here, so that means there's no variation in the z direction. So at most, what we can have is that the z velocity can really only at most be a function of the radius, right? That's the only thing it could vary with based on what we've set the problem up to be. So when I come down here and I write this out, I've got the z velocity on the left face here and on the right face, they're going to be exactly the same, right? Because the duz dz term is 0. So what I'll have here is on the left-hand face, it'll be uz times whatever the mass flow rate is coming in. And that'll be a negative because it's the mass flow rate coming in through the left side. So that term is just on this side. So it's uz coming in, and the mass flow rate is negative because the velocity and the normal vector are in opposite directions. And then going out through the right-hand side, the velocity there is still uz because it only varies in the radial direction. It doesn't vary in the z direction. And the mass flow rate out there will be a positive m dot. So when you add these together, it just comes out to be 0. Okay, so that's pretty straightforward. The body force term in the z direction we're saying is 0. There's no gravity to worry about in the way I've set up the problem. You could include gravity if you wanted to, but for the standard Poiseuille flow, there is no gravity, so we'll ignore that. So that just leaves the surface force term. Okay, so for the surface force term, let me redraw the picture of the control volume. So we have I'm going to look at it from the side. Again, this is dz here. And what we have on the left-hand side is we could have a pressure force that's acting on the side. So I'm going to draw this part. This is our dr distance, right? It's dr on both of these. Remember, what we're looking at here is this kind of annulus. So I'm just looking at the annulus from the side. Again, this is r out to there. Okay, so we could have a pressure force acting on the side of this. Remember, this pressure force is acting all the way around the surface here. So actually, instead of me drawing two little pressure force vectors, I'm going to erase those. I'm just going to draw it like this. But that pressure force is acting on this entire kind of green highlighted area. And so if I say that the pressure at the center is P, then the pressure on this side is going to be P plus dp dz times minus dz over 2. That's the pressure on that side. This is this idea again, if the pressure at the center is P, I start with that pressure. I see how pressure varies as I move in the z direction because I'm going from the center to the left. That's in the z direction. And I multiply it by how far I've moved in the z direction, which in this case is minus dz over 2. And then I can do the same thing on the right-hand side. Bp plus dp dz times positive dz over 2, because as I go from the center to the right, I'm moving a positive dz over 2 to get over to that side. Okay? So those would be how my pressure varies. And then I have to do the same kind of idea for the shear stresses. Now there's going to be a shear stress acting on the inner face here. So I'm just kind of showing it up here. It's on the inner circumference. And then there's going to be shear stress acting on the outer circumference. Let me highlight those in a different color. Let me use orange. So I've got the outer face, and then there's kind of like an inner face there. Again, it'd help if I was a better artist. But on those orange faces, I have shear stresses. So let me draw a positive shear stress on the outer face. That positive shear stress will act in the positive z direction. So that's a positive radial face acting in the positive z direction. If you don't know what I'm talking about there, you need to go back to your strength of material notes to understand the sign convention for shear stresses. But that shear stress would be tau rz. It's the shear stress acting on the radial face pointing in the z direction. And it'll be, actually, let me skip for a moment, and I want to do the negative one first. The shear stress on the negative face. The shear stress on the negative face is this one. So this one's incomplete at the moment. I'm going to come back to it. But let's say that the shear stress on this negative radial face there, let's call that one tau rz. It's on the radial face pointing in the z direction, so that the one on this outer face will be the shear stress I start with here, which is tau rz, plus how much that shear stress changes as I move in the radial direction times how far I've moved to get to that outer face. So if the shear stress on the inner face, that's this inner orange bit, is tau rz, then when I go to the outer surface, it'll be what I started with plus how that stress has changed as I've moved in the radial direction times how far I've moved to get in the radial direction. That distance is dr. Okay, so hopefully you understand that. And again, the sign convention or the nomenclature for shear stresses is this is the stress on the radial face in the z direction. Okay? And both of these are positively drawn shear stresses. So those are my surface force terms. So let me expand them back over here in my momentum equation. So let me start with the pressure first. So on the left face, we have that pressure force that looks like this. It's acting on the area 2 pi r dr. That area is this green face here. So that's what the pressure is acting on. And that's pointing in the positive z direction. That's why we have a positive out front here. And then we have this pressure force. That one's acting in the negative z direction. So that's going to be a minus p plus dp dz times a positive dz over 2, acting on the same area, 2 pi r dr. Right, again, it's this green area. That's what this pressure is acting on. All right, so hopefully you understand those pressure surface force terms. Now we have to do the shear stress terms. So let me do the inner shear stress first. That one's acting in the minus z direction. So that's going to be a minus. That shear stress is just tau rz. And then the area that one's acting over is this inner orange area. So that's going to be 2 pi r times dz. 2 pi r is just the circumference, and dz is the distance down the length of the pipe. And then we have this outer shear stress that's acting in the positive z direction. So that's going to be positive tau rz plus d tau rz dr times dr. And then that's acting on that outer orange area. So that'll be its circumference, which is 2 pi times r plus dr times the distance down the length of the pipe, which is dz. Okay, so hopefully you understand that this area is the area of the outer orange surface. Now we can go ahead and do some simplification here. You'll see that this pressure will cancel with that pressure, so that's helpful. And then there'll be this term here, just like with the conservation of mass expression, we're going to have to expand that out and simplify it. So we'll do that in just a moment. In fact, let's just do it here. So let me expand out the pressure terms. So that'll be minus dp dz times 2 pi r dr dz. So that's what we get when we combine this term with this term. You'll see that this has a negative there, and then there's a negative here, so that's where we get the negative. Both have a dp dz. They both have a 2 pi r. You can see that there. And then there's the dr dz terms, dr dz. And they add together, so the 1/2s just add up to 1. Okay. Then let me go ahead and expand the shear stress terms. This is tau, minus tau rz 2 pi r dz. And we'll have tau rz times 2 pi r dz plus tau rz 2 pi dr dz plus d tau rz dr times 2 pi r dr dz plus d tau rz dr times 2 pi dr squared dz. And hopefully I did my algebra correctly there, but this whole expression here is just expanding out that term. Okay, so hopefully I did my algebra correctly there. We'll find out in a moment, I suppose. But you can see some things cancel out here. For example, this term cancels with that term, so that makes life a little easier. The other thing is you'll notice this is a higher order term, right? We have a dr squared times a dz, so that's a much, much smaller term than everything else in here, which is just a dr times dz kind of quantity. So that's a higher order term. We'll neglect it because it's so small. And so what we're left with is minus dp dz times 2 pi r dr dz plus tau rz 2 pi r, I'm sorry, 2 pi dr dz. Let me just double check. Yeah, that should be right. Plus d tau rz times 2 pi r dr dz. All right, so a lot of algebra, some bookkeeping to keep track of. But now we can substitute everything back into the linear momentum equation up here. You'll see the first term again is just 0 because it's steady state. The second term is 0 because the linear momentum coming in and going out of the control volume are the same. We have no body forces in the z direction. And the surface force terms turn out to be a combination of pressure and shear stresses. Okay, so let's go ahead and substitute that in. It's going to look pretty much the same as what I just wrote. So I'm just recopying the previous line. But that whole thing adds to 0 when we put it back into the linear momentum equation. And then if you look at this for a moment, you'll see that we have a 2 pi r term in all of these, and a dr dz term in all of these. So we can, I think I dropped a dr. Let's see, this should have, let me fix it. It should be 2 pi dr dz. That's this one right here. But if you look here, again, we have the 2 pi times dr dz in all of these, 2 pi dr dz. So those can cancel. We can divide through by those because in general they're not 0. So we'll do that. Minus dp dz times r. And then we'll have tau rz plus r times d tau rz is equal to 0. Okay, we're making, and I made another mistake now that I look at it. This should not have been, you probably picked up on this already, but this should not have been a dz. It should have been, oops, it should have been this, it should have been a dr there. Apologize for that. I'm doing this all on the fly, so this is, I'm not looking at notes or anything like that, so I can make some mistakes here and there, but I'm catching them hopefully. Okay, that's what we should have. At this point, again, if you look at it long enough, squint your eyes and whatnot, you'll see that this term can be written a little more compactly as d over dr times r tau rz, right? Because if I multiply this or carry this derivative through on the r, like dr just is 1, then I have the tau rz term there. And then if I carry the derivative through on the tau term, then I get that times r, which is there. So again, we can write this a little more compactly like this. Okay. We're making good progress. May not look like it, but we are. Okay, at this point, what I want to do is make use of our Newtonian fluid assumption. So at the very start of this, I said my fluid is going to be Newtonian, so it's right up here. So that gives me a way to write the shear stress in terms of a velocity. So for a Newtonian fluid, that tau rz stress can be written in the following way. It'll look like that. It'll be, this is the most general way that we can write the shear stress on the radial face in the z direction. It's the dynamic viscosity times how the radial velocity varies with respect to z plus how the z velocity varies with respect to r. But we know that the radial velocity is 0, so we don't have to worry about that term. So it's just mu times duz dr. And so I can take this and substitute it in right up in there, right? So let's go ahead and do that. Okay, so now we have that expression. I'm going to go ahead and pull the dynamic viscosity out. I'm going to assume that the viscosity is not a function of the, well, actually, you know, at this point, I'm just going to leave it as is. Let me leave it here, but later on we'll assume that the dynamic viscosity is a constant. So we won't, it'll come outside a derivative in just a bit. But at this point, we can leave it as is. One little sort of math thing that we're going to do here is remember that the z velocity really can only be a function of radius. If I go back up here, remember we argued this right up here, that the z velocity is really only going to be a function of the radius. With that in mind, this partial derivative here can really be written just as a regular ordinary derivative. Same sort of thing with this one, since this, everything in the parentheses here is, you know, it's just a function of radius. Mu is a constant, so we don't have to worry about this. This is only a function of radius at most. So this will be an ordinary derivative, and that will be an ordinary derivative. The dp dz term is just a constant. Remember we said way back up here, it's a pressure-driven flow. The dp dz is a constant. We can just leave it as like this, but if you think about it for a moment, I said there was no variation in the theta direction. So the dp d theta would be 0. I'm saying it's steady, so there'd be no dp dt term. I'm saying that it's there's no variation in the radial direction because there's no radial velocity, there's no radial gravity component, so there is no dp dr. So really, we can write this one as an ordinary derivative as well. So let's go ahead and do that. So this will, if I expand this out with that in mind, and then just do a little rearranging, I'm going to have d over dr times r times mu duz over dr is equal to r times dp dz. So I just did a little bit of rearranging there. Let me integrate both sides with respect to r, right? I'll just integrate both sides with respect to r because of that. And so I'll get this expression. Okay, and then I'll divide through by the r on both sides. And then I'll go ahead and integrate both sides again with respect to r. Let me go ahead and divide by the mu as well while I'm at it. Actually, when I integrate that, this should go to a 4 and not a 2. This will become a c1 over mu times a natural log of r plus a c2. So that's now what my velocity profile looks like. It looks a little strange. It's like a parabola with a natural log term in there with a couple of unknown constants that come in from our integration. So we're going to have to clean that up in a moment. Okay, let me just go back and double check that I've done everything correctly here. Just reviewing my algebra. Okay, I think, yeah, I should be in good shape. Okay, so now we're at a point where we need to apply some boundary conditions. So one obvious boundary condition is that we have no radial velocity. I like to write these in words, so let me start with that. So no slip at pipe wall. So that's my first boundary condition. So that means that the uz velocity at r is equal to capital R is 0. All right. And then the second boundary condition, this one's a little bit trickier. You can think about it two different ways. The second one's actually going to occur along the center line. So right along the center line of this pipe, where r is equal to 0, if you go back to our expression here, if you take the natural log of 0, it goes off to minus infinity. It's undefined. And again, we know that the velocity should not go off to an infinite speed along the center line. That makes a lot of sense, right? So we can't possibly have this term here if we have flow along the center line. So that means that in order to have a finite velocity flow, we must have c1 equal to 0. So I can write that as or let me just write it this way. The magnitude of uz is finite at the center line. That's the center line symbol. So that means what that'll end up meaning is that c1 has to be 0 because we can't have this natural log term going to 0. Another way you could actually view it is you can say that the shear stress along the center line, because we expect the flow to be axisymmetric. Remember, this is a pipe flow. And there's nothing in this geometry that makes us think that the flow is going to lead, like the velocity profile won't be axisymmetric, right? Since the pipe has no variation in the theta direction, we can rotate this pipe any direction we want and it should look the same. So that means we expect to have an axisymmetric flow, which then means that along the center line we would expect the velocity to either be a maximum or a minimum, right? Because we can't have the maximum or minimum off the center line because then it would no longer be axisymmetric. So if we have any sort of maximum or minimum, that means it has to happen along the center line. So that means that this expression would have to be 0 along the center line, right? So along the center line, that's where r is equal to 0. So this term is fine. That just goes to 0. But this one would blow up to infinity, which we can't have. We can't have duz dr being infinite at the center line, right? We said if it's a maximum or a minimum, duz dr would have to be 0. So we can't have this one blowing up to infinity, so that again means that c1 has to be 0. Okay? So let me take both of these expressions here. Now we know that c1 is 0, so we don't have to worry about that. But this one here, what that'll tell us is that we have 0 is equal to 1 over 4 mu dp over dz times capital R squared plus C2. So that means that C2 has to be minus 1 over 4 pi. I'm sorry, 1 over 4 mu times dp dz times R, capital R squared. So then if I substitute back in, we're going to get the following. Or let me just rearrange it one little bit here. I just like to rearrange it so it looks like that. So that is now our velocity profile we just derived. And if you look at that for a moment, you'll realize it's a parabola. It's a paraboloid, actually. If I draw the velocity profile here, and this is our radial direction, when I have little r is equal to capital R, then it's 0. So our velocity profile would be 0 at the walls. And then the maximum will occur when little r is equal to 0, and that the maximum velocity will be this quantity. So it'll look like that. And then since it's an r squared kind of an expression, it looks like a parabola. So that is our velocity profile for this Poiseuille flow. It's a parabolic kind of profile. Okay, and just keep in mind, if I call this the z direction, dp dz in this case would be less than 0, because that means that the pressure over here on this side, let's call this pressure P, and then over here the pressure would be like P would look like this, whatever the length is. Let's call it L. We'll say this distance is L. So this would be the pressure over here is P. Here's the pressure some distance away. It's the pressure you start with plus how the pressure changes as we move this distance L to get over here. So if we want the flow to go from left to right, this pressure needs to be smaller than that pressure, right? We want to push the fluid from left to right. So that means that dp dz would have to be 0 to get the flow to go from left to right. And if dp dz is less than 0, then that makes this positive. Hopefully that makes sense. Okay, so now at this point, once we have the velocity profile, we could find, let's say, like the shear stress at the wall, for example. If I wanted the shear stress at the wall, that would be the tau RZ stress. That'd just be mu times du z dr. And if I want it specifically at the wall, I would evaluate it when r is equal to capital R, right? Because I want it at the wall. So that would be mu times minus 1 over 4 mu dp dz, and then I'd have times 2r. Right, because what I'm doing is I'm taking the derivative with respect to r, so, oh, actually, it'd be minus 2r here. So simplifying that, the mu's cancel out, the 4 and the 2 and the negatives cancel out. So I'm going to get r over 2 times dp dz. So that would be my shear stress at the wall. Okay, so the shear stress at the wall is really kind of related to balancing the pressure gradient to keep the flow fully developed, so it's not changing as I move downstream. If you think about it in this problem, when we did the linear momentum equation, the only thing we had in here were surface forces. So what we have is a balance between pressure forces and shear forces. It's that pressure, it's that force balance that keeps the velocity profile unchanging as we move downstream. So it's really the wall shear stress is balancing the pressure in some way to keep it, the velocity profile, from changing. If I wanted to get the volumetric flow rate through the pipe, for example, I could do that as well. The volumetric flow rate would be taking our velocity profile, uz, that's just this velocity, multiplying it by an area over which the velocity doesn't change. That would be a little annulus. And then I'd integrate it as r goes from 0 to capital R. You've seen that sort of thing before. So this would be like my little bit of area through which the velocity doesn't change. So I could evaluate that. I won't do that here, but you can plug in and evaluate it. That's not too hard. So once you have the velocity profile, you can find things like the volumetric flow rate. You can find the wall shear stress. You can find the average velocity. The average velocity would simply be just taking, you want the volumetric flow rate to be the same whether you're using the real profile or the average velocity profile. The average velocity profile would look like this. It's the average velocity times the area, total area. So you could find the average velocity then by just taking q divided by pi r squared, where q is just that expression up there. So you could evaluate that as well. I'm not going to do it here, but hopefully you get the idea. So we're at the end of this video lecture. It's run a little bit long, but just to recap, what we wanted to do is find the velocity profile for a type of flow known as a Poiseuille flow. A Poiseuille flow is just a pressure-driven flow through a circular pipe. Okay, so we set up what our geometry is that we're interested in, and then we applied conservation of mass. That one, conservation of mass, just told us there was no radial component to the velocity. Right, that's kind of what we got down here. We sort of knew that going into it, but I just wanted to show you the derivation to get that. But then the real action happens in the linear momentum equation in the z direction. And ultimately what it came down to was really a force balance, surface force balance in the z direction. A whole lot of algebra, making use of the fact that we're dealing with a Newtonian fluid, and then more algebra, a little more calculus, applying our boundary conditions, one of which is no slip at the wall. The other one is that the velocity and the shear stress, that they have to be finite at the center line. And when all is said and done, you get the velocity profile. Okay? So we'll go ahead and end the video lecture there.